In this video, we're going to talk about something called differential equations. So this is a very big area of mathematics. It's extremely useful in the field of applied mathematics, so for modeling different physical systems. And it has a very basic idea now that we've done antiderivatives and integrals, but they can get very complicated. Okay, so we're going to talk about differential equations. So first of all, what is a differential equation? So it's an equation involving some unknown function, okay, f of x, and some number of its derivatives. Okay, so some examples of differential equations might look like dy dx is equal to e to the x. Okay, so that's a derivative is equal to e to the x. Or maybe you have y prime is, I don't know, ln of x plus 7, okay, minus 2. Okay, it could look something like that. Again, only a first derivative equaling something to do with x's. You could have something more complicated. Okay, so maybe 2y prime minus y double prime plus x equals 0. Okay, we're not going to solve ones like this, but here we have a first derivative and a second derivative. Okay, so you can have any number of derivatives involved. So that's what a differential equation looks like. The reason why they're so useful is because it's often, I think I mentioned this before, it's often easier to collect data that predicts the rate that something is changing rather than the actual quantity. Okay, so when you're predicting the rate, that means you're predicting a derivative. So your model is for the derivative, and then you have to solve that to find the quantity. So that's where differential equations come in. And we've actually already done most of this. Okay, so for instance, we already know how to solve this differential equation. Okay, so dy dx is equal to 3x squared minus 2x. We already know this, okay? You might not believe me, okay, but we know how to do this. So what we want is we want the y, okay, to be some function of x so that dy dx, or y prime, is equal to 3x squared minus 2x. Okay, so we want the derivative of our y to be equal to 3x squared minus 2x. So what that means is that my y should be the integral of this derivative with respect to x. So what I want to do is take the antiderivative of 3x squared minus 2x. So then I find that my y, or y of x, okay, so as a function of x, is going to be x cubed minus x squared plus some constant of integration. Okay, now notice that with this c here, there's infinitely many solutions for y. Oops. Because we have one for each c. Okay, but we could check that we got the right thing by taking the derivative. Okay, so it's going to be, if we take the derivative with respect to x of this function, whatever our c value is, we get 3x squared minus 2x plus 0. Okay, so we get, it has the right derivative. So that would be the solution, or a solution. In fact, it's all the solutions with the plus c there, to our differential equation. So the derivative equals 3x squared minus 2x. Okay, so we already saw that each value of c in the solution and all the other ones we did gives a different solution. So our differential equation has infinitely many solutions. So when we include the plus c, we call it the general solution. Okay, so that gives all possible solutions to our differential equation. Okay, so when we have all possible solutions, that's when we have the general solution. So the form that we just had was a derivative is equal to something to do with x. So notice that this side only had x's. This is a form that we've seen before. Okay, so if you have a form of your differential equation is a derivative is equal to a function that only has x's. Okay, so maybe I'll just write here. So if there's only x's on this side, then your y function is going to be the antiderivative, okay, the indefinite integral of your g of x. Okay, so that is what we did already when we first talked about indefinite integrals. Okay, it's the same idea. And again, like we did before, if you're given an extra piece of information about the function, so this is called the initial condition, then we're able to find the exact c value that we need. Okay, this is called the particular solution. Okay, so you have the particular solution when you have an extra piece of information about the function. Okay, and here we call that an initial value problem. Okay, so you might see that phrase, initial value problem. So let's do an example of this type. So suppose the population P of a flock of birds is growing exponentially, so that we know that the rate of change of P is equal to 20 e to the 0.05 t, where t is in years. We want to find P in terms of t if we know that there were 20 birds in the flock initially. Okay, so this piece of information here, this is our initial condition. Because it's some extra information about the flock. Okay, and what it says is at time 0, okay, so P of 0 we know is 20. So what we want to do is find P of t. Okay, now again, notice that we have a derivative with respect to t, and this side is only t's. So this is the form that we just had. So that means we know that P of t is equal to the indefinite integral of our rate with respect to t. So we just want to take the antiderivative, so I can pull out the 20. Okay, now you might want to use substitution here. It depends how comfortable you are with these antiderivatives. But if you did, you would take u to be the exponent, and then du would be 0.05 dt. So that means that 1 over 0.05 du is equal to dt. And your integral, you would have 20 integral e to the u times 1 over 0.05 du. Okay, and then you'd have to solve for that. I'm just going to jump to the answer because because it's a constant times t in the exponent, we should maybe be able to do this. Here. So what it's going to be, the antiderivative is going to be from e to the 0.05 t, but because I'm going to get that extra factor of 0.05, I'm just going to divide by it out front. Okay, and then we should have our plus c. So 20 divided by 0.05 is going to be 400. So it's 400 e to the 0.05 t plus c. Okay, so that's our P of t. Okay, now this part here we would call the general solution, because it has the plus c still. Okay, but we can find the particular solution because we know that p of 0 is equal to 20. So that means that 20 is equal to 400 e to the 0.05 times 0 plus c. Okay, so that means that 20 is equal to 400 times e to the 0. E to the 0 is 1. So that means that 20 is equal to 400 plus c, which means that c has to be negative 380. So that means our particular solution, p of t, should be 400 e to the 0.05 t minus 380. Whoops. Okay, so that would be our particular solution. Okay, now this is something we already did. Okay, so there's nothing new yet. Okay, so the problem with this part comes when we have more than one variable, okay, or the other variable. So far, all the differential equations we've considered have one variable, okay, and in particular, they were in terms of the variable that the derivative was in. Okay, but this doesn't always happen. So when you have other cases, there's very many different methods that you can use to solve them. One of which is useful, is called separation of variables. Okay, now this doesn't always work, but in our class, it's the only other method that we have. So if you can't just take the antiderivative, then you should be able to use separation of variables. Okay, so that in our class. That's not true in general. Okay, the differential equations get very complicated, and there's many, many different ways to solve them. So to use separation of variables, what we want to do is think of, like we did before, as dy over dx as a quotient of differentials. So that means that dy and dx have individual meanings, and they can be treated individually. Okay, so then what we're going to do is rearrange the equation so that each variable is contained to its own side. Okay, so this is hence the name. Okay, so the first step is essentially, separate the variables. Okay, so what you're going to have after you do this is some function of y times dy is equal to some function of x times dx. Okay, so we want all the y's on one side, okay, and all the x's on the other. Okay, now you want to be careful to keep keep dy and dx in the numerator. So maybe I'll say on the top. So you don't want to divide by dx or divide by dy. Okay, you want it to be times those things. So just be careful. And then what we're going to do is integrate both sides. Okay, so once you have them separated, we're just going to take the indefinite integral of each. So on one side, we're taking it with respect to y, and on the other side, we're taking it with respect to x. Okay, and that's how we're going to solve these equations. Now, my note here is, again, like I said, it is not always possible to solve this way. If you can, we call the differential equation, which I sometimes shorten as DE. We call the differential equation separable. Okay, But in this class, that's the only type that we're going to have. Okay, so you don't have to worry about the more complicated ones. So you should be able to separate them. So let's try an example. So let's say we want the general solution of the differential equation. So notice that I have dy dx on one side, okay, equals some function that has both x's and y's. Okay, so they're mixed up. So what we want to do is we want to try and separate. Okay, now we want to keep dy in the top, so we would prefer to have y's on this side and x's on this side. So that dy is on the top and then dx is going to be on the top when we move it, because we're going to have to multiply by dx. Okay, so it's better to try and do that. Okay, so our first step is to separate the variables. Okay, so I'm going to multiply both sides by y squared. Okay, because that's going to move it from this side on the bottom. Those are going to cancel out. Okay, so I'm going to have y squared times dy dx is equal to x squared plus 1 over x. Okay, and then my next step, I'm going to move the dx over. So now I'm going to times by dx on both sides. And that's going to give me y squared dy is equal to x squared plus 1 over x times dx. Okay, now I can integrate both sides. So I'm just going to add the integral in here. So the left side is easy because we just have y squared, so we can use the power rule. So remember, we're integrating with respect to y. So y is our variable here. So this is going to be 1/3 y cubed. Okay, technically we should have a c here. I'm going to call it c1. But on the other side, I can't integrate right away. I'm just going to simplify it a bit. So you might think that you want to use substitution here, but we can actually simplify, and we can write this as two fractions added together. Okay, so this is actually the integral of x squared over x plus 1 over x dx. And x squared over x is just x. So I get x plus 1 over x dx. Now I can integrate this. So this is going to be equal to 1/2 x squared plus the integral of 1 over x is ln absolute value x. And then I have some other constant c2. Now to I want to solve for y. So here I can actually, so I know relationship between x and y now, but I actually kind of want to solve for y. So I'm going to subtract c1, okay, on both sides. That's going to get rid of it over here. So I'm going to have 1/3 y cubed, and actually, yeah, okay, is 1/2 x squared plus ln absolute value x. Now, I'm just going to call this C, oops, I already have a C2. Let's just call it C3. Okay, so write it here. So C3 is some other constant that's going to be C2 minus C1. Okay, I'm only doing this to show you that you don't actually have to care about these different C's. Okay, they're always just going to end up being a constant. So now what I'm going to do is times both sides by 3 so that the 3 on this side cancels with the 3 here, because then I'm just going to have y cubed. Okay, so I times everything by 3. It's going to be 3 over 2 x squared plus 3 ln absolute value x. And then 3 times c3, okay, that's some other c4. Okay, some other constant. Now here's where it matters where the constant, actually I'm going to, instead of calling it C4, let's just call it C, because it's going to be the last time I change it. Oops. Okay, so it's just C. But now here's where it matters. So in order to get y by itself, I want to take the cube root. So all this stuff that I've done to the C doesn't matter because I've just added a constant or multiplied by a constant, okay, divided by a constant. None of that matters. What does matter is when I move C. Okay, so here I need to take the cube root of both sides to solve for y. So that means that my C needs to be inside the cube root. Okay, so it's this whole thing cube rooted. So the C has to be in the cube root. Okay, so this would be my general solution here. Okay, so I have y equals some functions of x. You're not always able to solve for y, but here we could, so we should. Okay, let's move on to what we're trying to get to is real world examples. So a lot of real world examples require this idea of proportionality. So we say that R and S are proportional to each other if there is some constant k so that one is k times the other. Okay, so R is k times S. So k we refer to as the proportionality constant, because it's sort of the proportion that they grow together. So this occurs quite often. So one example is when you invest money in a compound interest account, one that's compounded continuously. Then we know that your investment grows at a rate that's proportional to the amount of money that's there. So if you have $A at any time t, okay, so A of t is the amount in your account, then we get a differential equation that relates A and t, okay, and they're proportional to each other. Okay, so let me just highlight here. So we know that your investment will grow at a rate, so your investment will grow at a rate, so we see this word proportional, to the amount of money that's there. Okay, so what that means is that the rate of change of your investment, so this is the rate, the investment changes. This amount is proportional to the amount in your account, which is A, or A of t. So because it's proportional, we know that there's some constant k, so that the rate is equal to k times A. Okay, so this is a constant of some. We don't know what it is, but it's some constant. So for this, we can find the general solution. Okay, now we want to be careful. So k is a constant, not a variable. Okay, it's just a number. Treat it like a number. But, so you might think that there's only one variable on this side. Okay, but that variable is A, not t. So that means we want to separate the variables here. So to find the general solution, we're going to separate the variables. So that means I want to move A to the left-hand side. So I'm going to divide by A. So I'm going to have 1 over A times dA dt is equal to k. Now, if you want to put k on the left-hand side, it's a constant. It can go on either side. But I normally keep it with the t because I want to solve for a eventually. So it's better to already have it with the t. But it could be on either side. Okay, then we're going to multiply by dt so that I have 1 over a times dA is equal to k times dt. And now I can integrate both sides because I have all the a's on the left and there's no t's, okay, but all the t's on the right. So the integral of 1 over a dA is ln absolute value a. The integral of k is a constant. It could come out of the integral if you want. So the integral of 1 dt is t. So I'm going to have k times t. And then I only need one constant. So I'm going to put it on the t side. So I have ln of a is equal to kt plus c. And I want to solve for a. Okay, so now we want to solve for a of t. So if I want to get rid of a ln, I have to use e. Okay, so it's going to be e to the ln of a should be equal to e to the kt plus c. Okay, now notice the c has to go in the exponent because it's moving. Okay, we're moving it, it has to move. So e and ln cancel, so I just get absolute value a is equal to e to the kt plus c, which I could actually write as e to the kt times e to the c. So when you have addition in the exponent, it's like multiplying with the same base. And then we could just make a note that e to the c is some other amount, some other constant. So I'm going to call it p here. So that means that my a of t in absolute values, actually, we could write it as p times e to the kt. Okay, that would be my general solution. Okay, now in terms of the investment, P ends up being a of 0. So if I plug in t equals 0, so this is what we call the principal, if you've done any finance. Okay, so it's the initial investment. So it's the amount that you put in initially. And K actually ends up being your interest rate on your account. Okay, you don't have to know that, but that's what ends up happening. So the rate that your amount changes is proportional. The proportionality constant is actually the interest rate in this case. So, and that's actually what I said here. So the proportionality constant K is known as the growth constant or the decay constant, and when t is 0, we get a of 0, which is p e to the k times 0. So that's p e to the 0, which is just p, okay, and that is your initial investment. I should remember what is coming, so I don't repeat myself, but anyway, that's what happens. So the sign of k makes a big difference. Okay, if k is positive, so we had a of t is p e to the kt. So if k is positive, that means that your exponential is growing this way. Okay, because e, that's what e looks like, with e to the x. Okay, it's like that. So that means that your quantity, which in this case is your money, okay, but your quantity is growing. Okay, here's where we call k growth constant. Okay, now if k is less than 0, which sometimes happens, okay, not for interest, but for other things, then your exponential function is flipped along the y-axis, so it looks like that, which means that your quantity is shrinking. Okay, and in this case, we call k the decay constant. Okay, so your amount should be shrinking. So that might happen when you're talking about, say, radioactive decay, which behaves like this. Okay, cell growth is another one where it can be modeled this way sometimes. So there's lots of examples that share this property, that the rate is proportional to the amount present at time t. And so we have the differential equation of a certain form, which means we get a solution of a certain form. So if P of t is the amount of some quantity, and the quantity is said to grow or decay at a rate that's proportional to the amount present, then we get the differential equation dp dt is equal to k times p. Okay, for some constant k. Okay, in order for it to be a solution, P of t, just like we just went through this, P of t will have the form, so it always has the same form. So I'm going to call it P0 times e to the kt. Okay, where P0 is the amount or number of the quantity at time 0. Okay, now P of 0 is a constant. Okay, and when it's unknown, that means that we have the general solution. Okay, and if we have an extra piece of information so that we can determine it, then that's when we have the particular solution. Okay, so there's just one more thing I want to mention. So as a model, this form is not always realistic over the long run, okay, especially for populations, because normally we think that the area can only support so many things, right? So it might have some maximum level. Okay, so if we suppose that the area can support some maximum population n, and maybe that the population grows at a rate that's proportional to how close we are to this maximum, then we get a different differential equation. Okay, so if we say the population is p, okay, so P of t is the population size at time t. Okay, then dp dt, so the rate the population grows, is proportional to, but here it's proportional to how close the population is to the maximum. Okay, so what that's going to be is the maximum minus the population size. Okay, so this is our proportionality constant. Okay, but the thing that we're proportional to is the how close we are. So that's the max minus the current population. That's going to tell us how close we are to that maximum. Okay, so now if we try to solve this one, it's a little bit different. Okay, n is a constant. Okay, it's some maximum that we know the area can support. Okay, so we want to treat it like a constant, but because it's sort of attached to the p, we're going to have to move it with the p. Okay, so if we wanted to solve this, the first thing I would do is divide by n minus p. So I'm going to have 1 over n minus p times dp dt is equal to k, and then I would times the dt over, so that I have k dt. And now I can take the antiderivative, or the indefinite integral. Now here I think I will show you the substitution. So for the left-hand side, I'm going to let u be n minus p. So then du is the derivative of this, which is with respect to p. Okay, so that's negative 1 dp. So that means that negative du is equal to dp. So then my integral is going to be 1 over u times negative du. Okay, so the negative can come out. So then I get negative ln u equals kt plus c. Okay, I'm going to move the negative to the other side and plug in the u again. So that's n minus p. This is going to be negative kt plus... the plus here, you can make minus c if you want, okay, but it doesn't actually matter because c is a constant. Now I want to get rid of the ln, so I'm going to use e. So n minus p is e to the negative kt plus c. And now if I solve for p, p of t is going to be n minus e to the negative kt plus c. Okay, now like we did before, we could change e to the negative kt plus c. So this is actually e to the negative kt times e to the c. And maybe e to the c we write as, I'm going to call it m this time. Okay, some constant times e to the negative kt. Okay, so this is what our general form would look like in this case when we have some maximum, which maybe makes sense for more populations because they can't usually grow unbounded. Okay, so this might be a better model for some things. Slightly different, a little bit harder to solve, but following the same strategy as before. So all we used was the fact that our rate was proportional to some amount. Okay, so here though, just the amount was not just p, but it was n minus p. So how close our population was to that maximum. So the closer we get to the maximum, the rate is going to slow down. But the further we are, the further apart we are from it, the faster it can grow because there's lots of room for it to grow. Okay, so that's the idea here. So that's a very brief introduction into differential equations.